here is the solution for homework 19. And let's see, what did I do? I created a problem where we have this disc that weighs 30 pounds and diameter is 3 feet, but it has a radius of gyration of 1.25 feet. I wanted you to get used to the radius of gyration thing. And it's attached to this block that's 75 pounds. And this cable is inextensible, can't stretch, massless somehow, so we don't have to worry about the mass of the cable. That make it a complicated problem. And it's passing over this frictionless, massless sheave, which is like a pulley, right? And the block is on the slope. It's at 55 degrees, so this is not to scale. And it's got a coefficient of kinetic friction of 0.25, and the friction is enough here so that this thing doesn't slip or spin. It's got enough friction so this is going to roll, and it's released from rest. So we want to find the acceleration of the block, the tension in the cable, and then I ask what changes if the sheave has mass, and I want you to answer that. I'm not going to give it to you as part of the solution. But I do require it, and I'll take points off if you don't answer it. I just want to want you to think. Okay, so here we go. Let's go. I think I forgot to write down what my find was. I'll write down my find. So I want the acceleration of A, and that means it's a vector, right? And then B, I want the tension in the cable. So what's the first thing to do? Let's get some properties going on here. So first off, we need to get the moment of inertia of this disk. So I gave you the radius of gyration. Therefore, you should take the mass times the radius gyration squared. All right? And so the mass is going to be 30 divided by 32.2. Remember, we got to turn these into slugs. And then we're going to use the feet because that's our system right there. So we have 1.25 squared. So what did I end up with? 30 and 32.2 divided 1.25 squared, and multiply it, so I get 1.456, and these are slug feet squared, right? That is what the mass moment of inertia units are in United States, woohoo, units. All right. What else do I want to try to get? Well, first off, I have two parts to this thing joined by a cable, and even though I want to get the cable tension, I'm going to do that as the second thing. First off, I want to get free body diagrams and inertial response diagrams of each of these parts, and they're going to be connected via the cable. We also might want to do, okay, so maybe that's the first thing I'll do. I don't want to make it too complicated, but also I'll try to be methodical. Here's your FBD and IBD of, let's see, I don't have to make it full size right here. I'll make it 2 here. So here's this guy, and here's this guy of this, and they're equal to each other. And I'll use my, so we have this force, that guy coming down, and let's see, we have the weight. So we have the weight of C, and therefore we have the normal force of C, and then we're also going to have a friction. So the friction force is going to go this direction, right there, right? F, C. And now, okay, so I think those are all the forces that we would be seeing that are going to be acting on here. And always a good idea to put the coordinate system as part of this thing, right? So here's our X and our Y. And now we're going to have an acceleration right here. So it's going to be the mass of C times the acceleration of C. We're also going to have an angular acceleration, right? So I'm going to write it out this way right there. right? So it's going to be accelerating this direction, and that's going to be I of C alpha C. And I'm going to go ahead and write these over here. So I'm just going to kind of do this sort of in columns. And we'll do the FBD. And of this guy on the block. And let's see. I'm going to go ahead and make a rotated coordinate system, if you'll recall doing this, the X prime and the Y prime. And we have a cable tension, Ft, right there. We will also have weight of A. We'll have a normal force of A. And this is going downwards, so the friction is opposing it. So it goes that direction right there. And so we have FA. And I think I have all the forces. I think so. And we're going to predict this thing is going to accelerate this down here. So it's the MAAA. Now there's a number of things that are connecting these parameters together. So that tension right there is the main one that's connecting this guy and this guy. This acceleration here is going to be the same one as that acceleration, right? That cable moves that cable right there. So that's a dependent motion, but it's simple enough that we know that's going to happen. And we can think of that as kinematics, right? This is a kinetics problem, but we have kinematics that are joining some things. We also have rigid body. It's very simple here, but this acceleration is related to that acceleration. So we're going to see that, and that's going to simplify some things, right? So we're going to have a lot of unknowns, but we're going to be able to simplify them. So I might want to do this one first. It's going to take up a lot of room, but I could do this one. I could just set it up here. So I'm going to say the sum. Oh, I don't want to do the sum of the forces. I don't want to find this friction force. I don't really need it. For one thing, yeah, it's not going to really help me out all that much. I think that's true. I'm rethinking that. I don't think I need that friction force. I don't think I want it. No. All right. So let me get this moving along here. I didn't solve this problem ahead of time, and maybe that's not the greatest idea. It'll be all right. I'm not worried about it. I think when I get over to this side right here, that's going to be good enough. Boy, maybe I should pause this and I could do the problem out and then just transcribe it. It's probably smarter to do that. I don't know. I'll take the sum of the moments about, and I'm going to create this point right here. I'm going to create this point and call it D, right? So that's my D. I just needed to call it something. It's going to be equal to yeah. So we're going to have the mass of C times AC, right? No, sorry. I just wrote that first. Let me write that first. Note that this, I'm just going to write this, okay, I forgot. This is how I do it. I should start over, but I'm not going to. The effective moments about D, right? So when we go to write this out, we have to make sure that we're putting all of these in here. So we're fortunate that everything here, all these cancel out because they're all passing through D. And we're going to make, we decided that for whatever reason, we're going to keep going with counterclockwise is positive. So we're going to take Ft times the radius of this right here. And I'm going to use values this time. So that's going to be 3 divided by 2, right? Because it's 3 feet in diameter. And nothing else causes a moment here. And that's going to be equal to IC times alpha C, right? I said I was going to, I lied. DC divided by 2. Okay, and that's going to be minus because it's going clockwise, and this is minus MC AC. All right, but that is just the inertia. We need to have it through the effective one, so it needs to be going through this. So that's going to be DC over 2. Right, so there you go. Yeah. Now for this one, I'm going to go the sum of the forces in the y prime direction is equal to mass times acceleration in the y prime direction, and we know that equals to 0. So this angle of the thing, right? So this angle right there and right here, this is the 55 degrees right here, right? So that's 55 degrees. And we're going to get FNA minus the weight of A times the cosine of theta in there, and nothing else, right, equals 0. So FNA is equal to 75 times the cosine of 55, which is going to be 43.02 pounds. Therefore, the friction force of A 0.25 and 43.02, and we get 10.75. 10.75 pounds. Now we want to set up the other part of this, which is going to be the sum of the forces in the x prime direction, is mass times acceleration in the x prime direction, going that way. So we have a negative Ft minus FFA and plus WA sine of theta is going to be equal to MA AA. So if I put stuff in there, negative Ft minus my 10.75 plus my 75 sine, I think that's right, hope so, of 55. I didn't actually check to see if this was going to be a large enough number, but we'll see. Okay, I'm hoping everything works out. I think everything will work out. And then I'm going to have my mass is 75 divided by 32.2 times my AA. So Ft, the force due to the tension here, is going to be, okay, so 10.75, I'm going to go 75, and the sine of 55 times, right, so I'm just double checking here. Yeah, we're going to subtract that out, right? It's like 50.68, and that's going to come over onto the other side and be negative negative, and that makes that negative. So that ends up being 50.68, and that's going to end up being minus, and I'll do the 7532.2 divide on and get 2.329 acceleration of A. All right, so that we're going to keep that. We have two unknowns, but we have, this is one of our unknowns up here, right? So we have a negative ft times r3 divided by 2. It's going to be equal to negative 1.456 alpha c minus, and now I'm running into problems with how much room I made here. It's going to be 30 divided by 32.2 acceleration of c, and then we're going to have 3 divided by 2 right in there. Where all these negatives are going to cancel out. That's great. And but here we can take an ft, because I'm going to set these equal here in a minute. So that's where I'm going to come through here. And I'm going to divide, so that's going to be 1/2. So I'm going to divide through by that 1/2, which is going to get rid of that, by the way. So that really just affects this. So I have 1.456 divided by 1.5. I didn't plan that. 0.9707. And then that becomes plus, and then just 30 divided by 32.2. Right, because that's going to cancel out that, yeah. So 0.9317 acceleration of c. All right, so we have two equations, and we have four unknowns. 1, 2, 3, 4 unknowns. But we could take kinematics, and my keyboard here. Take my kinematics. Simple kinematics here. And we also will take a very simple, that the acceleration of c is also going to be equal to alpha c times dc over 2, right? Because there's no slipping, that means that here, about this point right here, this is a tangential acceleration about this point. So just alpha times r is going to give me that acceleration. So, oops, come on, wake up. All right, I'm going to go to another page because I'm going to have to do some more writing. All right, and so I guess I can fill a little bit of this stuff in here. One continued, combine. I guess I'll call this equation 1, equation 2, equation 3, and equation 4. Combine 1 through 4. Through 4. There you go. So I could do it in one step. 0.9707 alpha. So maybe I should have made this one. So therefore, alpha c is equal to AC divided by DC over 2, right? So I can stick him in here, and I can, so I'll call him 4, and I can combine him with 3 right in there in one step, so to say that the acceleration of A, which I'm subducting into there, is, and then take 3 divided by 2 here, right? So that was this guy. That was me substituting in for alpha, and then plus 0.9317 for acceleration of A is going to be equal to 50.68 minus 2.329 acceleration of A. And I should be able to solve for the acceleration of A, which is the first thing that I wanted to try to get. And I think I'm going to be okay. So, yeah, this guy's going to come back over to there. And hopefully this is not going to be a negative number. Ooh. Let me double check something. I'm a little concerned. It should be accelerating. I don't want to get a negative number. I'm concerned about the negative numbers. Okay, well, let's just see what happens here. I'm concerned about the negative numbers. Tension that way. Accelerate. And I know it's got acceleration downwards right here. I'm going to pause the video. Damn you. Math. I'm totally golden. Okay, so good. All right, that's gonna be negative. It's gonna bring back over there. Duh. Ugh. All right, so I'm gonna divide this one by 1.5. Gotcha. And I'm gonna add them to here. Gotcha. And then I'm gonna add them to here. Gotcha. And then I'm gonna divide 50.68 by that. So 50.68 and divide. And I'm going to get 12.97 feet per second squared. Now, make sure that you realize anytime that you have feet per second squared, you can compare it to gravity, right? So it's a fraction of gravity, right? So you can see that, okay, that makes sense, because gravity, the things that drive in it, so it better not be going fast, have more acceleration than gravity. And now we can go back and we can put this into, probably the easiest is into equation 2. So we can find what the tension is going to be. So 50.68 minus 2.329 times 12.97, and so we get 2. Wait, did I already have that in there? I already had that. I already had it in there. That's nice. Combine, and then take 50.68, and we end up with 20.47 pounds. Anything else that we need? No. Okay, so that was A and B, and I told you C you need to find yourself. So we're going to answer this as 12.97 feet per second squared, 55 degrees, right? It's acceleration one vector. And the tension, 20.47 pounds. You don't give it an arrow because it depends on which side you cut the cable, and you're looking, you wouldn't know which one. Okay, so these are the answers. And we have ourselves a solution. I don't know. Should I put the A and the B inside the box? This time I didn't. I don't know. So let's be done with this one.